Hello everyone, and today we're going to talk about representing relations and functions. So here we go. Alright, so let's talk about our definitions, the things we need to know. Okay, so a relation is a mapping or pairing of input values with output values. So again, we're going to talk about input and output a little bit later on this slide, as if you're looking ahead. Okay. Now, a function is a relation for which for every input there's exactly one output. Okay? If one input has two or more different outputs, that's not a function. We'll talk about that too. I've got a nifty little joke for you to help you remember that. Now, here we go. This is the big thing. Okay? The domain is the set of input variables, also known as the independent variable. And again, it is going to typically, let me get rid of that. That looks terrible. Okay. It's typically our x value. Okay. Because that's usually when the variable that we're putting into an equation or function. Okay. Now the range values is the set of all output values. That's called our dependent variable. And typically, by process of elimination, is going to be our y's. So we typically will say that, okay, domains are our x's, which is also our input, like I highlighted earlier. So domain is input, which is also the x's. And the range values is also the output values, which is typically our y's. So kind of a way to remember all that. Domain is the x, range is the y. All right, so let's continue on. All right, so here we go. I'm going to shrink this down a little bit here so we can work. Okay, so we got a couple different things here. We're asked to identify domain and range. Looks like we're giving a mapping format, and then we're asked to identify is it a function or not. So let's start with the easy stuff. Okay. All right, so here we go. Let's start with our domain values, our x values. So that's going to be the 3, the -1, the 2, the -2, and the 0. Okay, so if I were doing a mapping of this, like this has demonstrated here, okay, so we're going to have our 3, we have a -1, we have a 2, -2, and 0. Okay. Now, then we had our range values. These are my y's. So the 2, the 0, -1, 1, and 3. Okay. So we're going to put that in. Let me zoom back in on that. Whoop. So we're going to have the 2. We're going to have 0. We're going to have -1. We're going to have 1 and 3. Now, if we were asked to list these things, like it says right here, domain, we'd have 3, -1, 2, -2, 0. Range values is going to be 2, 0, -1, 1, and 3. Okay, now if I was showing the mapping relation, because that's what this thing right here is, it's showing you a map. Okay, so what you're going to see, let me zoom in on that. What you're going to see are arrows, okay, for the ordered pair. So for like this first one, we have the ordered pair 3 to 2. Okay, so we're going to draw an arrow from 3 to 2. Okay, our next relation is -1 to 0. Okay, we have 2 to -1, so 2 to -1. We have -2 to 1. And we have 0, 3. So that's what our mapping would look like of this demonstration. Now, the overall question, is this relation a function? Okay. Now, to do this, to answer this question, it's going to kind of go back to an old joke my father used to tell. Okay. Now, to understand the joke, you're going to have to listen very, very carefully to this joke. Okay, so get ready, get your listening ears on. All right, so here's the joke. Pete and Repeat are in a boat. Pete falls out. Who's left? Now, most of you would say Repeat. So we would go again. Pete and Repeat are in a boat. Pete falls out. Who's left? So again, it would be Repeat, and the process would keep going and going and going. Now, it's funnier, obviously, when you have an audience that I don't have right now. So, well, in all actuality, it's a pretty horrible joke. But what does that have to do with relations? Well, now, if our domain values, and again, this joke relates to the question, is it a function? Again, is solely for the x values. Our domain. Our y's can do whatever we want. We don't care about what y does. It's all about what x's do. If the x values Pete, okay, then it's a function. Now, what do I mean by that? Well, I go back to the joke. If I were to say the joke, if Pete and Repeat were in a boat and Repeat falls out, who's left? Well, you'd say Pete. And that'd be it's not really a joke. It's okay, that's just a statement. Great. But the point of the matter is the joke stops. That would be an example of a function where my x's do not repeat. So x do not repeat. Okay. Now, if my x's repeat, then it's not a function. It's just a really bad joke. Come on. So x repeat. Okay. So, based on what we're seeing here, okay, if I were to look solely at the x's, now again, I don't care what the y's are doing, I could care less. If I look at my x values, I have a 3, a -1, a 2, a -2, or a 0. So, is this a function or not? Do my x's Pete or repeat? In this case, since none of my x values repeated, this is a Pete, so it is indeed a function. All right, let's move on. All right, so now we're given a mapping. Are the following maps a function, yes or no, and why? Or if not, we have to identify why. Now again, remember, a mapping is just giving you how the ordered pairs go. So for instance, this is our x, this is our y, right? So if I look at this first one, okay, I'm going from 1, follow the arrow, and we're going to 4. So this is the ordered pair, 1, 4. The next one, I'm at 2, follow the arrow, and I go to 4. So this is the coordinate 2, 4. Then we go back to here. I'm at 3. We follow the arrow to 3. So this is the ordered pair 3, 3. So now, looking at my x's, okay? I have an x value of 1, 2, and 3. Do my x's peat or repeat? In this case, they would peat. Therefore, this is indeed a function. Okay. Now, if I come over here. Okay, so let's start our mapping. Okay. So we're going to start. I'm going to use a different color here for the highlighter. So if I start with 1, I follow the arrow, I go to 3. So this is the ordered pair, 1, 3. Okay, let's go this. We have 2 going to 4. So this is the ordered pair, 2, 4. Okay. Now again, we're going to start at 2. We're going to go to 5 this time. So this is the coordinate 2, 5. And then we have 3 going to 6. So we have the coordinate 3, 6. Okay. So now, looking at our x's. I have a 1. I have a 2. I have a 2. And I have a 3. Do my x values peat or repeat? And in this case, as most of you probably just noticed, my x values repeat. This is not a function. Now, you have to then explain why. That's what the direction said. So it's all because of this right here. X value of 2 repeats. And that's your explanation. Okay. Let's move on. All right, now we're given a table. And again, same thing, asked to identify, is this a function or not? And if not, we have to explain why. So again, realizing that this is another way we can write ordered pairs. Okay, well, let's just go across and make our ordered pair, right? So this is the ordered pair. Okay, come across here. Okay, so this is the ordered pair. 1, 2. Okay, come across here. This is the ordered pair. 1, 3. Okay, here, come across.
I got flour to you.
Oh, you got flowers for me? Thank you, Gwen.
It's very big.
That is a big flower, you're right.
Smell it.
Oh, it smells so nice. Why don't you show Mommy?
No.
Why not?
So, I can't.
Oh, you can. So now let's look at our x values. We have, oops, didn't turn the highlighter on, sorry. So we have a 1, we have a 1, we have a 4. So, do my x values peat or repeat? And again, they repeat. Therefore, not a function. Now, explain why.
Oh no,
X
my house.
value
My house.
of 1
Daddy.
repeats. What?
Daddy, my house.
Okay. There you go, pumpkin. All right. So now let's move on to the other question. So let's slide this over. Okay, so again, let's take a look at this one. So this ordered relation says we have 1, 7. This one says we're doing 5, 3. This one says we're doing the ordered pair 4, 7. Now, at this stage of the game, some people will say this is not a function because I got these guys right here. They're the same, they match, so therefore it's not a function. But remember, folks, that doesn't mean anything.
No.
Those are the y values. We only worry about the x values. So, between 1, 5, and 4, do my x's peat or repeat? And again, we say they peat, therefore this is a function. Oops. All right, so let's move on. All right, now we're doing the vertical line test. Okay, it says tell whether the relation function if and only if no vertical line intersects the graph in more than one point. That's the vertical line test, which basically means in English, if you were to take a straight edge, let me zoom in first. So let's look at this first graph. Okay. Okay. So if we were to take our first graph and we take a straight edge, so any straight edge will do. So here we go. There we go. Now it has to make a nice vertical line, okay, which my lightsaber does. What?
I got flowers.
Yes, you do. Thank you.
Smell it.
Yeah, it smells nice. Okay, so the vertical line test. So again, what you're going to do is going to go from left to right, okay? And again, you can only hit the equation or the line with the side of the lightsaber in one place at a time. The second you hit more than one place, it is not a function anymore, okay? So let's scroll through. So we go across. See how we're good. We're only at one place at a time. Now we got this point here, but that's still okay.
There you go.
Oh, thank you. So we keep going across, keep going. All right, keep sliding across. And notice how at any point on this line, we only hit the lightsaber at one position. So therefore, this is indeed a function. So function. Okay. Okay, so let's go to the second graph. Let's slide over here. Okay, I'm going to back out a little bit just so the lightsaber will work better. So, here we go. Looking at this next one. So I break out the lightsaber. Okay. Now, I'm going to start off. I haven't touched the graph yet. I'm good. So right here, I'm good. But notice now, my graph hits at 2 points at the same time, starting from basically all the way at the start of the graph. I'm hitting 2 points at a time, 2 points at a time. The second you hit your graph in more than one place with the edge of the lightsaber or the edge of a straight edge, this is no longer a function, because the reason being is you have x values, as you can see here and here at 1. You have x's repeating themselves. Basically what you have here is you have an ordered pair at coordinate 1, 1, and you have coordinate 1, -1. So again, you have x values repeating themselves, therefore it's not a function. That's why the lightsaber here is going to hit this twice at the same time, okay, which you cannot have. So in this instance, this is not a function. Okay. All right, let's move over to the third one. Now this one I'm going to zoom in on. Okay. This one's going to be a little trickier to see. Okay. So here we go. I'm going to break out the lightsaber. Now it's going to look like it, but again, I'm only touching one place at a time. One place. Still only one place at a time. And again, as I go across here, it's only going to be one place at a time. The whole time. See, you're only one place at a time. Okay. Now it looks like it's more than that because again the lightsaber is pretty thick, but again, it is only hitting at one place at a time. So this is again a function. Okay. All right, let's move on. All right, tell whether this is a linear function or not, and then evaluate the function for x. Now, linear function, okay? things you are looking for. Okay, it is not, it's easier to say if it's not a function linear if you have the following things: x squared or above. Okay, because that makes a parabola, makes a graph that looks like this. If you have absolute values, okay, that makes a V-graph. If you have, here, let me scooch this, I need more room here. If you have radicals, okay, that gives you a graph that looks like this. Okay, you're looking for these things right here. Okay, so if you have any of these three things, it is not a linear function. Okay, so let's go to our example here. So we look up, first off, in this graph, or this function right here, do we have any exponents? The answer is no. Do we have absolute value? The answer is no. Do we have radicals? The answer is no. Therefore, this is a linear function. So this is linear. Okay. Now they find f of 5. So we're going to put 5 in for x. So f of 5 is equal to 3 times 5 plus 1. Therefore, f of 5 is equal to 15 plus 1. Therefore, f of 5 is equal to 16. Okay? So there's that one. All right, so let's look at the next one. I'll scooch this down. Come over here. Okay. Tell whether this is a function, then evaluate the function for the given x value. So next, okay, do we have exponents? The answer is no. Do I have absolute value? Yes, I do. It's right here. Okay, whoops. Forgot to turn on the highlighter. Sorry. We have absolute value right here. So this right here is not a linear function. Okay, it is a function, it's just not linear. Okay, so now from here, I'm going to kind of scooch the slide over so I have more room to work. Sorry. Okay, so now from here, let's do this up. Let's do the math. So I'm going to put negative 9 in for x. So g of negative 9 is equal to the absolute value of negative 9 plus 2 plus 3. Okay, so g of negative 9 is equal to the absolute value of negative 7 plus 3. Therefore, g of negative 9 is equal to, I snap the absolute value bars and get positive 7. Therefore, g of negative 9 is equal to 10. And there's that one. Okay. All right, let's go on to the next one. All right, so here we go. Tell whether it's linear, and if it's not, explain why. All right, so for the first one, we're looking for, do I have any exponents? No. Do I have absolute value? No. Do we have radical symbols? The answer is no. So this is linear. Okay. Now this next one, okay, this one is not going to be linear. Oh, shoot. Okay, this one is not linear, and the reason being is this. Okay, well, you say, well, gee, you told me before I'm looking for 3 things. That's true. Those are the telltale giveaways here. This one right here is kind of a sneaky one, where it's not as easy to see, but you do have the x in the denominator, okay? And the reason why this would not be linear is because the second I put x is equal to 0, I wind up with a 0 in the denominator of a fraction, which creates a non-existent solution. So if you were graphing this thing, your graph would actually have a hole in it. Okay? So this is not a linear function. So that's another thing. So our four things now, okay, is exponent. Okay. Second thing we discussed was absolute value. Okay. Third thing we look for is radicals. And now the fourth thing we look for is variable in the denominator. Oh, come on. Okay. So those are our four key pieces. Again, I did the last slide only with 3, so you look out for those other things. But we do have this extra thing we have to worry about too. Now moving on to the next one. Okay. So, do we have exponent? And yes, I do. So this is not a linear function. Next one. Do I have exponent? Yes, I do. So not a linear function. So the only linear function we had was the first one. All right, so let's move on. All right. Last but not least, I'm assuming we are identifying if it's a linear function. So here we go. Last one. So to start, do we have exponents? The answer is no, we do not. Second thing is, do we have absolute value? Yes, we do. Therefore, this is not a linear function. No. All right, the next one. Let's take a look at that one. Okay. Do we have exponents? The answer is no. Do I have absolute value? No. Do we have radicals? No. Do we have variable in the denominator of the fraction? No. Since I answered no to everything, this is indeed a linear function. Yes. Okay, the last one. Do we have exponents? The answer is no. Do we have absolute value? No. Do we have radicals? No. Do we have variable in the denominator of the fraction? Well, we have a fraction, but is there a variable here? The answer is no. So therefore, is this a linear function? You bet it is. This is yes. Okay? Alright, so that's the end of this video. Hopefully you learned a lot, and we will see you next time.